Okay, I think the recording has been started. So I'm going to explain you the hands-on on the multiverse optimization algorithm and how to code it in the Python. So first of all, I'm going to run my Python code on Google Colab environment. So you have to search it first, and you can see here we are getting the result of this first link. So click on it and click on new notebook. Okay, so in this cell we are going to write our code. So we will study example of applying multiverse optimization algorithm in Python using a simple problem for minimizing this sphere function. So first of all, I'm going to import numpy. So we have to import the numpy library, which we will use for the numerical operations. So I'm going to run this code. Okay, so the tick sign indicates that our code has been executed. Now I'm going to add the other line of shell for writing the code. Now here I'm going to define this sphere function as our example objective function. So this is a simple optimization problem where the goal is to minimize the sum of the squares of the input values. So let's try the code. Sorry. Okay. Now we have to define the multiverse optimization function which takes the following inputs like objective, lower bounds, upper bounds, number of universes, number of iterations. Now let me write it and then I will explain you. We are going to initialize number of universes as 50. And number of iterations as 100. Now we have to create an array to hold all these universes. So I'm going to create an array. Okay, so here we have created an array to hold all the universes. Now we have to find the initial best universe. So I'm going to write the code for it. Okay, for the simplicity, I'm going to write the comment create an array to hold all the universes. Now we are going to find the initial best universe. So best universe sorry. Okay, so here we have defined the initial, how to find the initial best universe. Now we have to start the optimization loop. I think I should explain the meaning of each thing. So here the objective, so this objective is the objective function we want to optimize. The lower bounds is a numpy array with the lower bounds for each variable. The upper bounds is a numpy array with the upper bounds for each variable. And the num universes is the number of universes, that is particles, in the algorithm. So we have initialized here as 50. And number of iterations is the number of iterations to run the algorithm. So we have defined here 100. Now we have created an array of random universes with shape, that is num universes, and number of variables with the given bounds. Now we have to start the optimization loop. So let's start the optimization loop. I think I missed some part. Hmm. Okay, let me figure it out. Okay, yeah, that's correct. Now we have to update each universe. So we can write now we have to create a new universe by moving the current universe a little bit. So I'll write the code for initializing the new universe. So this is the way to find or create a new universe by moving the current universe a little bit. Now, we have to make sure the new universe is still within the bounds. So let's code for it. Now, um, okay, okay, yeah. Now, if the new universe, sorry, is better, we have to update the current universe. So let's write the code for it. Now we have to find the best universe. I think some error is there. Let me clear it out. Okay. Now we have to return the best solution. So sorry. Now we have to set the bounds for the sphere function. This thing is okay. Now we have to set the bounds for this sphere function. So lower bounds is equal to np dot array and upper bounds np dot array okay. Now we have to apply and we have to find the best solution. So best solution sorry lower bounds upper bounds now let's print the best solution is okay. Now let's run this code. I hope this will work out. Okay, so the best solution we have obtained is this one. Now let me explain to you from the beginning. So first we have to import the NumPy library, which we'll use for numerical operations in this cell. And here we have defined this sphere function as our example objective function. So this is a simple optimization problem where the goal is to minimize the sum of the squares of the input values. Now we have defined the multiverse optimization algorithm function, which takes the following inputs like objective. So the objective function we want to optimize, lower bounds, which is a NumPy array with the lower bounds for each variable, and the upper bounds, which is also a NumPy array with the upper bounds for each variable. Num universes is the number of universes particles in the algorithm, which we have initialized as 50. Number of iterations is the number of iterations to run algorithm, that is which are defined as 100. Now we have created an array of random universe with shape num universes and number of variables, and with the given bounds. Now we have to find the best universe according to the objective function. Now we have to start the optimization loop and run it for a specified number of iterations. And we have to keep on updating each universe by iterating through them. Now we have to create a new universe by adding a random amount, what we call scaled by the distance to the best universe to the current universe. Now we have to clip the universe to make sure it stays within the specified bounds. So if the universe is better, which has a lower value, according to the objective function, update the current universe with the new universe. So after all iterations, we have to find the best minimum universe according to the objective function and return the best universe as the solution. Now we have to define the lower and upper bounds for the sphere function problem as NumPy arrays. So after running this code, we'll apply the MBA algorithm to the sphere function problem and print the best solution it finds. So this is the sphere function is a simple optimization problem used for demonstration purpose in this lecture, and you can replace it with an objective function specific to your own purpose like additive manufacturing or for any real world application.